Hey everybody, in this series of videos we're going to talk about naming organic molecules, and we're actually going to talk just very cursorily about naming organic molecules. Why don't we get started here? And so to get started we should talk actually about hydrocarbons. Hydrocarbons are compounds that contain only carbon and hydrogen. Now, organic molecules are those that contain carbon. Now, if you are taking biology, you'll know that usually organic molecules have some combination of carbon, hydrogen, oxygen, and nitrogen. But if you're a biology or if you're a chemistry person, typically the only qualification is for the compound to have carbon in it. There are some minor exceptions, but for the most part, organic compounds are those that contain carbon. Okay. Typically, they contain other things like hydrogen. Well, most of the time they contain hydrogen. Sometimes they contain oxygen. Sometimes they can contain nitrogen. Okay. But hydrocarbons are those organic compounds that contain only carbon and hydrogen. Now, there's a whole boatload of different types of hydrocarbons. We're only going to talk about a couple of them here. Okay, so let's start by talking about alkanes. Okay, now this ending will become important, but in a minute. But let's talk a little bit about alkanes. So alkanes are hydrocarbons, those compounds that contain only hydrogen and carbon, and they don't have any multiple bonds. And so carbon one of the beauties of carbons is that it can form long chains with each other. And then what we can do is we can then fill up the molecule with hydrogen. Now there's a couple of little gems in here that I'm hiding that I'm not having you write down as notes. But carbon will always have 4 bonds, and one of the reasons why it's the basis for life is because it can form long chains. Okay, actually, as far as I know, carbon is the only compound that can form infinite chains that are infinite length virtually, and not sacrifice stability. So that makes it very interesting and very conducive to life. Now, I have this little formula here about 2n plus 2. Now, if we count up the formula, okay, here's what we know. The number of carbons, 1, 2, 3, 4, 5, C, 5. And then H, if we count hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of hydrogens is 2n, where n is the number of carbons, plus 2. And that is true with all alkanes, all straight chain alkanes, okay? And so if we have something like butane or propane, this is propane, like what you put on your, or what you use to grill out when you're using a gas grill, okay? How many carbons are there? There are 3. And how many hydrogens? Well, we would predict that there would be 8. And indeed, when we count 1, 2, 3, 4, 5, 6, 7, 8, we have 8 hydrogens. And so this formula allows us to recognize alkanes pretty straightforwardly. Okay, now notice all the carbons are what we call sp3 hybridized carbons, or sp3 carbons. Okay, so there's 1, 2, 3, 4 bonds all around each carbon. Okay, carbon has 4 bonds, always in organic chemistry. Okay, and because they're sp3 hybridized, or because they're sp3 carbons, there's what we call free rotation. Okay, these carbons here, this carbon here is able to rotate around and come up here, and so it can spin freely. Okay, now let's take a look at alkenes. Okay. Now, alkenes are interesting. This is now when we start getting into something called a functional group. Okay, a functional group is when we have something that's not a single bond, carbon or hydrogen. Okay, but alkenes are only carbon and hydrogen. Okay, so they are hydrocarbons. Okay, and now they follow the rule, the 2N rule. So if we have C5, the number of hydrogens is going to be twice that at C5H10. Okay, now alkene, whenever we see that ENE ending, we're going to know that there's a double bond somewhere. Okay, and so if I take, let's say, propene, okay, this is what the carbon backbone looks like. This is what the carbons look like. And then when we put the hydrogens in there, okay, we get this. Now, the thing about this is, well, first of all, let's count. So now there's 3 carbons. Let me get rid of this formula. This one may be confusing people a little bit. Okay. Okay. So that's good. Okay, so we have C3, then 1, 2, 3, 4, 5, 6. H6, it follows that rule. Okay, so it follows the 2N rule. And we'll notice now that there are sp2 hybridized carbons. There's 1, 2, 3. They have bonds now, okay? they have multiple bonds. There's a double bond in there. That double bond is what makes it what we call an alkene, okay? Doesn't matter that there's single bonded everywhere else. As soon as there's one double bond, that makes it an alkene. And where there is a double bond, that locks that configuration into place. Okay, so there's no free rotation around this carbon. Okay, that thing is locked into place and can't move. Okay, there is free rotation here where this hydrogen can flop down here and spin around and spin around and spin around, but there's nothing here. Okay, it's because there's sp2 hybridized carbons. Okay, so if we can have alkenes, we can also have alkynes, and I was always taught it takes alkynes to make the world go round. Okay, and so alkynes are hydrocarbons that have only hydrogen and carbon, and they follow the 2N-2 rule. So if we again have propyne, which I'm familiar with, I used in graduate school all the time. Okay, let me draw the Lewis structure of this. Okay, and so, and keeping in mind that carbon will always have in it let's see, yeah, there we go. Okay, let me get rid of some of this junk here. Okay, good. And now let me go back to this. Okay, carbon always wants to have 4 bonds. Okay, only carbon and hydrogen. Now if we look at the formula of this, it's C3, but then it's H4. Okay, make sure my H and my 4 look different. Okay, and so it's C3H4 following the 2N-2 rule, where N is the number of carbons. 3 times 2, 2N is 6, minus 2 is 4. Okay, and alkynes are characterized by having triple bonds. So because there's a triple bond in here, okay, that triple bond makes that an alkyne. Now, a triple bond is what we call sp hybridized. There's only 2 bonds, so it only takes the s orbital and the p orbital to actually hybridize there to make that. And again, just like in the double bond, there's no free rotation there. Okay. Now, the last type of hydrocarbon that we're going to talk about here are aromatic hydrocarbons. And aromatic hydrocarbons are kind of interesting because and this is the most common one, okay, they're usually a cyclic hydrocarbon, and they alternate with double and single bonds, okay, and then again, remember carbon needs 4 bonds, so everywhere in here is 1 hydrogen, okay, and there's not really any pattern, even though this is C6H6. That's not a That's not an always pattern, okay? That it's always the same number of carbons as hydrogens. That's not anything that you want to follow. It just happens to be, okay? And so what happens here when you have alternating double and single bonds is we have something called delocalized electrons. Now, I wouldn't worry about what delocalized electrons are right now in a lot of detail, but what happens, I will give you the 30-second version, is that the electrons that are in this double bond, they can jump around, okay? And then in this double bond they can jump around, and then this double bond they can jump around, and then once they're here they can jump around. So these electrons that are in these double bonds here, not the single bond version, but just the double bond, they move around and they spin and they spin and they spin and they spin. And so they're not local between two carbons. They are delocalized. They go between all the carbons, okay? And so that's my 34-second description. So I think that kind of gives you an introduction to what hydrocarbons are and kind of how we determine what class, alkane, alkene, alkyne, or aromatic, what class those hydrocarbons fall into. So there it is, and have a great day.